think I'll come more often. And what I want to present today is the sort of experimental program of our group in Pelletron laboratory. And what we have been doing for many years is to studying making reactions with mostly weakly bound nuclei projectiles, and then we try to understand the dynamics of these reactions. And what we try to do is to measure as many channels as possible, and then we try to explain this in using the same potential and same kind of model, like to calculate all this stuff. So just from this very beginning, just more for the students, like what we do, like with the energies that we have available in our accelerator, like we mostly study, investigate reactions at energies that are around the Coulomb barrier. So we cannot go much above it for most of the reactions that we choose. And of course, like when these two nuclei are very far apart, then we only have this Coulomb interaction, but when they get together, then this nuclear interaction starts to pop up, and then at the end, if you add these two, if you just forget the centrifugal potential, for instance, then we have this, what we call the Coulomb barrier, and we are most of the time with energies around here, so around the top of this barrier. And then what we have is, in practice, is a projectile, which most of the time we choose weakly bound ones. And then we have a target, and then we do a reaction, then we put a set of detectors here. And what we measure is what comes out from this reaction, mostly. Like it's not very often that we can measure also the recoil or the target. So this elastic scattering is, of course, the overwhelming process. So most of the time we get elastic scattering cross sections. But even though they are very useful for probing this nuclear interaction, so this is very important ingredient in our studies. But then, besides the elastic scattering, we often measure other processes. Other process may occur, and then if you have like a lithium-7 on tin 120, for instance, and then we can have the excitation of the projectile or either the target or both, and then this is something that we can measure very easily. We may have also transfer, so we can transfer like a neutron or proton or deuteron or whatever it comes, and then we can have like stripping, we can have a pickup. So we, at the end, like we are going to produce like another species, and then this we can also measure with a certain, it's not so complicated like to measure. And then, of course, we can have complete fusion. This is something that we don't often do in our lab, but in principle it is possible for if you have like a good combination of projectile and the target. But then when it comes to weakly bound nuclei or even azotic nuclei, like if you go into this chart and then we pick lithium-6, lithium-7, beryllium-9, boron-10, and then we have a look at the binding energy of these systems, and then we can convince ourselves that all these are probably cluster nuclei, so they have this alpha structure, and then the binding energy, like for lithium-6, it's only 1.5 MeV for alpha plus deuterium. So we expected that this lithium have a large probability of breaking up. It may break up into alpha plus deuterium, and then it would be nice to measure these two particles in coincidence. And this is a bit complicated from the experimental point of view. So then if we move to this chart, then apart from this, we may have also the breakup of the projectile, and then we can have what we call the sequential complete fusion on if the target just absorbs those two fragments, but then we can have also incomplete fusion, so only one of these two fragments are absorbed by the target, and then we can have what we call the no capture breakup or elastic breakup when we have both fragments that are not captured by the target. And this is actually what we are interested for, like to measure these two particles in coincidence. And so if we go back to the 9, then this is we can have a look at these measurements that were done at the Australian National University by the group of Nanda Dasgupta and David Hine. And then they started this business long time ago, and they were measuring lithium-6 and lithium-7 and beryllium-9 on very heavy targets. And then they could, by doing this, measure the fusion. So they were producing like heavy nuclei that decay by alpha, so they could measure these alpha particles, the alpha decay, and then they could calculate or determine experimentally the fusion cross-sections, and then they could separate the contribution, what they call it, complete fusion and also incomplete fusion. And then they were always seeing that if you do like a calculation, then you have a less cross-section than you might expect. And then this, what they call this suppression, the scalar factor is related to the binding energy of the nucleus, very naively. And then if we, if you just look to this binding energies and this factor that is related to this suppression, then it's everything seems to be solved, right? And then many years later, we have done also for boron 10. And then I was there as a postdoc at this time. And then we could see also this reduction of about 15%. And then even for boron 11, we could see something. But this is a matter of debate. But anyway, like this, what we would consider like weakly bound nuclei are here in this group. And then many years later, they decided to build this very nice setup just to measure these two particles in coincidence. And then they make an experiment. They shoot lithium-7 on lead-207. They also did it with lead-208 and many other targets. And then they were expecting to see alpha plus triton in coincidence. So then we may imagine that the lithium-7 breaks into alpha plus triton, and then we would be able to measure these two in coincidence. And then, in principle, we could be able to calculate some cross-section, then we could compare like with some model like CDCC or whatever model we can use for just calculating this probability of this projectile breaking up and then these two particles flying away without being absorbed by the target, right? And then they were quite surprised because they have seen this spectrum here. So if you look, alpha plus triton is here, but then they could see also alpha plus deuterium and then alpha plus alpha, right? And then the explanation for this is the transfer plays a very important role in this business. So if we transfer like first a neutron from the lithium to the lead, then then it's possible to form lead-208, and then the lithium-6 would break into alpha plus deuterium. And then you can go the other way around. Like lithium-7 can pick up a proton and then becomes a beryllium-8, and then it splits into alphas like almost immediately. And then you see this very nice yields here. And then what we learn is that the nature is not much simpler as we would imagine, like in the beginning. So then this is then the large number of groups started this business of trying to measure these particles. And then, of course, like measuring this is complicated, but it's not so complicated. But then moving from yields, from events to cross-section, then it might be complicated. Right? Then it's not so simple. It's not so easy. Okay, so then we are here in this. This is in the University of São Paulo, like a few kilometers from here. And then we have an accelerator there, have a machine with 80 million volts. And we have a beam line that is dedicated to do this type of reactions, to study this type of reactions. So we started this almost 10 years ago. And then at this time, like we had the only couple of very old single PIPs, like single detectors, and we could not even measure the E delta E spectrum, so it was very complicated, like to separate events that were coming into the detector with the same energy. But then we could produce this very nice spectrum that we can see the elastic scattering. This was a boron on tin 120, and then we could resolve all these excited states from the target and from the projectile. So here we have the first excited state of the boron 10, and here two excited states of the tin 120, and we could also see some events that are related to the transfer of one neutron from boron 10, and then we form boron 11 and the tin 190. So that was the very start. And then we decide like to buy like a large area detector and then to improve a little bit our setup. So we had the only financial support for buying one of this SSD. So this is a very thin detector that is manufactured by Micron Semiconductors. So its thickness is about 20 micrometers. And then we have like 16 strips in this direction. And then we could buy like a very thick patch detector, which is about 1,000 micrometers. And then by combining this and this, we could have these telescopes which have 16 large, relatively large detectors. And then we decided like to put a mask in front of this just to restrain this area here. And then by repeating the same experiment, then we could produce this very nice spectrum. And then here we can see like the elastic scattering, and then we can separate this neutron transfer, and then we could see also very small amount of carbon, and then we could see beryllium 9. Also, we can see some beryllium 10 here, which is very interesting because then we have the beam is boron 10, and then we are producing beryllium 10. So it's probably like a charge exchanger process. And then we could see lithium 6, and lithium 7. This might be coming from the breakup. Also some helium 6 here, and then of course like a bunch of alphas. And then like if we remove the cross sections, we can have like elastic scattering cross sections here, and then like if we do couple channel calculations, and then we put as many ingredients as we can, so we add a lot of channels here, like transfer channels, inelastic channels, and then we use this the São Paulo potential as a bare potential, and then we can reproduce quite well this data here. And then this is for 40 MeV, boron 10 on T120 still. And then very recently, like we do like another experiment to complete this region here. And then we can see these points, and it's very preliminary, like we have to go back and reanalyze this data. But even though like it's seems to be, everything seems to be all right. And then if we do the same using boron 11 now, then we can see here that for energies below the Coulomb barrier, then everything looks all right, looks actually the same. Here we have like a difference of about 4 keV, like in the energy, so they have a mismatch here, and then this might explain part of this difference, but this is quite interesting. Like, if we go here, like at 37.5 MeV, then the boron 10 has like a dump here in this Coulomb nuclear Coulomb interference region, and then we don't know exactly how to explain this. Like we do like the best calculation that we can, even using CDCC, and then we still see this, the curve goes close to the boron 11 data, and there is no way that we can make this dumping unless like we put a very large imaginary potential, but then we miss the cross sections around here. So there's something funny, and that it seems to be around this energy. Like we go to 40 MeV, as I showed before, and then looks like that the data is following the trait of the calculation. It's something that we have to look. But anyway, apart from the elastic scattering, like we can also select other channels, and then we can get the cross sections for the inelastic scattering of T120. We can also see this is the 2+ state, this is the 3- state, this is the boron 10 excitation. We can reproduce this quite well. We can see also transfer here, and everything is possible like using these telescopes. Okay, then this is quite interesting. Like as I said, we can see beryllium 10 and beryllium 9, and if we take only the beryllium 9, like this is the projection is here, then we see like if you do just arguments thinking about the binding energy of this process, like the T120 plus a proton, then we can convince ourselves that part of this data is really populating the breakup, the continuum. So this might be related to the breakup of the boron 10. So of course, like we did not, we didn't perform any calculations in this sense, but if you put a line in here, then we can say that part of these events are related to transfer, like normal transfer, and this might be related to the transfer to the continuum. Right? So we see a bunch of these events. So then we have studied a relatively large number of reactions, like lithium 6 and 7, and boron 10 and 11, and several targets. And everything that we have done until this time here, 2023, more or less, 2 years ago, were like inclusive measurements. So we are only measuring one particle and then trying to guess what was coming out. So with this kind of measurement, the maximum that we can do is to have like a spectrum like this, and everything is mixed up. So then we decided to move over and try to do exclusive measurements, like from now on, since 2023. So now we have a list here of reactions that we want to study. Part of this has already been measured, and for that, like we need the basic requirements for doing these measurements. What we have to do, like, is to build like a more powerful setup for this. So we need detectors which have a large granularity, large geometric efficiency, and we want to have like as many as possible. Right? So at the moment we have 2 detectors working, and I want to show this. So what we have done is, like in 2023, we decided to dismount everything for now in chamber, and then we decided to start over. So we built like a new setup, completely new setup. Now we have a much better control of everything. And we bought like 2 detectors like this. So what we have here is the same kind of 16 strips tin detector that we bought from Micron, but then in the back, between these and the pad, we put a thick 16-strip detector that we also bought from Micron. So those have 400 micrometers, and then we just flipped this by 90 degrees, and by putting this together, we constructed this array, which has 256 pseudo telescopes. So each square of this has 3 by 3 millimeters, and in principle, like we have 256 telescopes in each piece of this. So you have 2 mounted at the moment. So that means that we have 512 channels to analyze. So we moved it from a system which have 8 or 9 pips to one that has 512 independent signals, pixels. And then, of course, like it's only 500. And then if we put another 2, it's going to be 1,000. We don't need like some artificial intelligence for doing this analysis, but we need some intelligence, right? And for that, we have very clever students. So they spend a long time writing scripts, and the complicated part of this business is to reduce the data and then end up with a number of spectrum that can be analyzed by like a human being. So this is not very simple, but they managed to do. And then at the end, when we look to one of these pixels, this is how this spectrum looks like. So the resolution is quite good. And so this is an experiment that we have done with lithium-7 on tin 119, more or less around the Coulomb barrier. And then we can see here, of course, this elastic scattering, but then we see in the elastic scatterings, we also see this neutron stripping, so we are forming lithium-6. We see, again, helium-6, so this is a proton stripping. We see, of course, alphas. We see tritons, deuterons, and protons, and we are very happy, we're very satisfied with this kind of spectrum. If we do boron 10, again, like at 40 MeV, then we have a much better resolution now, and this is only one strip, but if we calibrate this properly, then we can, of course, add it is only 1 pixel, but if we calibrate this properly, then we can add more than 1 pixel, because many angles are essentially the same, scattering angles, and that means that we can improve a lot the statistics of these events. So if we want to measure something that is complicated, like this 10 beryllium, for instance, that is not, that the cross sections are probably not very high, like we can measure this by less time, and then we can add the events of many strips around in a certain angular region, and then we can improve a lot the statistics here, and then we can do something with this data. So this detector is really very, very nice. And then, of course, at the end, what we want to do is to measure 2 particles in coincidence, not only 1 particle, right? And so what we have done so far is just a test, just to see if this makes sense. So instead of taking 1 pixel, like this here, right? This is the same spectrum. Right? If we take it, instead of 1, we take the whole detector at once, then we see this very blurry picture here, like everything is out of space. And that happens mostly because this thin detector is extremely non-uniform in thickness. So when we buy this detector from Micron, they say it's 20 micrometers. But then if you characterize this detector, and then you see the thickness of each of these pixels, then you're going to convince yourself that this may vary from 13, 14 to 25. And then it varies in the same strip. So this energy loss of this of the particle in the entrance, in the first stage of the detection, messes a lot this axis here, because we are going to have like particles entering with the same, basically the same energy, but hitting a detector which has like a factor of almost 2 in difference in thickness. And then we're going to see 1 particle pop in here and another 1 pop in here. And this is the sort of thing that we see. That's why we need to characterize those detectors and then do all this, all these scripts before using this spectrum. But anyway, this is not important here for this argument. And if remember, like now we have boron 10, so we expected this to break into lithium 6 plus alpha. This is one possibility. The binding energy is 4.5 MeV. So then if we take this, all the events that are heated the detector, we see this kind of spectrum. And then what we can do is to put a gate on this lithium-6 events. So all these events here are related to lithium-6. Right? We know that because we can export the lithium-6 quite well here. Right? So then, if you put a gate on this, we can sort only the particles that are coming in coincidence with those ones here. And then if we do that, then we see everything is quite clean, and we see helium-4 coming together. So this is a strong indication that this boron 10 is at least breaking into lithium plus alpha. It's, of course, this kind of stuff is not useful for extracting cross-sections, but it's a test of viability. And then, if we do the same for boron 11, like we shoot boron 11 in the same target at the same energy, then we have like this very nice spectrum of 1 pixel. We see all these events coming. We are producing like carbon 12. We have many inelastic states here. We have a neutron transfer. We have proton transfer, deuteron transfer, alpha transfer, and so on. And if we do the same business here, we put now a gate into lithium-7 events, then we would expect to see alphas if the boron 11 is breaking up. And when we look into here, it's completely empty. So we only see, mostly we see same particles that are coming in the same gate, just because we have like a large number of events like being produced by the combination of the thickness of our target and the intensity of the beam. So those are sort of those are not really coincidence, but those are only events that are coming into the same gate, which is about 5 microseconds in our electronics. Okay, so the idea is to start using these detectors like to actually measure these two particles in coincidence. It's not so simple with the sort of electronics that we have mounted now, because we don't have any information about the time, so we only get information about the energy, and time is important in this business. So we are buying like a new electronics, so we're going to upgrade our electronics and see if we can resolve this problem. So this is just to show like a very recent paper that have been published in PRC last month, 2 months ago, I don't remember. And here, for the first time, we have characterized these detectors. And so here we can see like the sort of a map of the thickness of this detector. So we see that the yellow ones are the thicker region of the detector. So if we measure that this is a strip, this is one strip, then we go from 18, 19 micrometers to 23. That's the maximum here. Right? So it's extremely non-uniform, and this is causes a lot of problems, like a lot of troubles in the data analysis. But this is something that we know how to fix. And if we do this, if we add events from different pixels in a proper manner, like take into account this kind of features of this detector, then we can see here like the spectrum of one single pixel here. This was carbon 12 on 119, I think. And we see here like elastic scattering, we can see here the neutron transfer, we see here the proton transfer. And then this is the events that come into one strip, but then if you add the events of the whole strip, so we have 16 pixels now, then we improve quite a lot the statistics. And then that was very complicated to see. We can see very well here when we add the events of this picture. So then we can extract this proton transfer cross-section very, very easily, like if we do this properly. Okay, so the forthcoming, like we are planning to buy a couple of more detectors and also to put digital electronics in our bin line. And then we are also mounting another detector that is called the Oscar. And this is a collaboration with our Italian friends. And so the idea of this detector is to use this very thin 16-strip detector that is manufactured by Micron. So we have this detector already. And then in the second stage is made of 16 silicon pin photodiodes. And then at the end, rather than having 256 pixels, we have 64 if we do the combination of these strips with these detectors here. So we are building 2 pieces of this. One is already mounted, so we have to test and now have to characterize this detector. It's a bit more complicated, like for the technical point of view, because the preamplifiers of this spin photodiodes are mounted inside the chamber, and we have to find a clever way for cooling down this during the operation. And this is not so simple. Like we don't want to put like water running into our setup. So we are looking for ideas. We have now this dissipator that is made of copper. And we are doing tests just to see if we are not going to burn this preamplifiers in a couple of minutes. I think we are not, like we are safe. But let's see. So, like just to summarize, like we have measured several reactions at our lab, and then we are being like successful in describing simultaneously all this reaction process, like using the same nuclear interaction, and we think this is a good benchmark, like for testing the nuclear potential models. And we have tried in the São Paulo potential so far, and the first version, the second version, everything seems to be all right. And then we know that these couple reaction channels, like they can give us like a reasonable description of the data, like we do this prescription, like we have the bare potential, and then we include many channels in our calculation. Then we use like a code like Fresco, and then we get out this cross-section, then we compare with the data that we can measure. Right? And then, of course, like we are convinced that the development of instrumentation is extremely important, and even more in our lab. It's a medium-sized lab with not many people around. So, if you want to be competitive and attract students, then we have to manage to develop like a competitive setup. Otherwise, we are going to be killed in a few years. Like we know that. And then at distance, of course, like students are very welcome for joining our research group. We may have a couple of fellowships that we can offer. So thank you very much for your attention, and thanks for the invitation.
Thank you very much. Okay, now paper is open discussion. Any question or comment? No comment or question?
I have.
Okay,
As usual. Leandro, thank you for this nice overview and the direction the Pelletron is going, the LAFNA is going.
LAFNA, yeah.
And I have just a curiosity, no? You showed beryllium 9, I think beryllium 10, boron also that you are able to produce. And I was wondering, for example, if you could measure, get information on, for example, the breakup of beryllium 9, that you have 2 alphas plus a neutron nearby, I mean, at low energy. Because the 2 alphas, I think you can measure.
Yeah.
Of course, the neutron, you should get the kinematics from somewhere and get some information about this system in the continuum. This is one example.
Yes.
Can
yes.
you do this kind of stuff?
Beryllium 9 is, if you want to measure the 3 particles, then it's more complicated, yes. It's complicated because the neutron is, it's complicated to measure just for this, right? I mean, if you have like 3 charged particles, then it would be relatively simple, that it's possible at least. Right? For measuring the beryllium 9, then we would need to have like maybe a larger neutron detector. We do like a neutron wall in our lab, but it's
but could
not
be 2 alphas and a proton.
The 2 alphas we can,
example,
we can measure 3 particles. Yes.
In low relative energies.
Yeah, in principle we can measure these 3 particles,
okay.
But then of course, like if you have 3 particles, then and we might need another setup. Like we may need like to cover like a larger area. Like if we think about the 4 pi, like we have at the moment we have 2 detectors that we can mount in anywhere, like in principle. Then we have to look into the kinematics, but they are large, but they're not very large. Like they are 5 by 5 centimeters. So we are not covering like a very large portion of this. I mean, the solid angle is not so large. And then if you have 3 particles, then it might be more complicated. I mean, it's easier like to miss one of these particles. But then it depends. And then but in principle, yes, like we have to think about it. Okay. Because this position of the detectors are also very flexible. So we have to mount this setup in a very clever way, in the sense that we may improve or increase the probability of picking up the 3 particles. But then measure this is not so complicated, but then going from what we observe to cross-section, then I would say it's almost impossible. Like I don't know how to do it. Okay. Then we need some clever model, like because the problem is not to, the problem is mostly to infer what you don't measure. So what you miss is the problem. Right?
Yeah, you could make the Dalits for that. Yeah. For example, to start with that.
Yeah.
As a function of the.
But in principle, it's possible. Yeah.
Leandro, with the improvement of your experimental setup, are you able now to measure angular distributions of separate states for transfer reactions at least?
Yeah. That's possible. Yeah, that's not so complicated. Because we can move these detectors. Without
because I remember in the past I have even done calculation for your data, but there was a bump of the states from this energy to this energy.
Yeah.
But you may be making errors in calculations in each of them.
Yeah.
And when you sum everything, you maybe have a good description of the experiment.
That depends in the what nuclei you populate at the end, the final state of the nuclei. And then, of course, like if you populate like a nuclei that has a lot of excited states, like very nearby, then it's impossible. Like then, of course, like we can separate this in slices, but each slice has about 1 MeV or maybe more. So depending on the case, we have a bunch of states inside this bump. So we cannot resolve each one.
Is there any perspective for the fusion in the future?
No.
Unfortunately, no.
No, I mean, we have a talk about this. Like, of course, like we can, what we can do now is something similar to what we do in Argentina with our colleagues, like the group of Andrés Arazi. So if we populate like a beta decay nuclei, then of course we can measure this offline gammas, and this is relatively simple to do. Right? We can measure the prompt gammas. Maybe like if we combine our setup, if the setup that zero is building, then we may have a chance. But I think we are very far away from this day. But anyway, it's.
Okay, so next question is Daniel.
Okay.
So I realize this was not what you built this to do, but is it possible to do, if you send in one of these light ion beams on, say, a lead target, is it possible to do Coulomb breakup with this setup?
Yes, it's possible to measure this, the Coulomb breakup. I'm not sure if it's possible to really infer or separate and say this is coming from the Coulomb breakup.
Right.
I don't think it's easy like to separate this Coulomb contribution to the nuclear contribution. Like we can always make arguments looking into distances and arguments like this. But everything is classical or semi-classical. I think that's from the quantum mechanics point of view, I think it's quite complicated. Because what we observe at the moment is charge fragments with a certain energy. And then, of course, like if we're lucky, then we can measure if we know angle and we know the mass and we know the energy, then we may try to reconstruct the kinematics and see, well, this is coming from this projectile, right? But then if it's related to Coulomb breakup or nuclear breakup, then I think it's more complicated. Unless we can see like resonances and if you have like prompt breakup and delayed breakup.
So I mean, you have obviously thought about this much more than I have, but maybe this is related a little bit to the question of angular information, right? So in principle, can you do this at very forward angles?
Yes. Yeah. You
just
have to be careful like to not burn the detectors, but in principle, yes. Mechanically, it's possible.
Okay.
Yeah.
And so, okay, I think that's all I wanted to ask.
But this is in principle it's possible. Like, and we also could try to do like some reactions in inverse kinematics, and that would favor this type of information. But then, of course, it's always a risk because you have to really be careful because the problem with these detectors is this: we have this entire strip. And then, if we think about this 3 by 3 pixels, like you see, okay, the solid angle is very small, so there's no risk. But then, actually, what we have is one entire strip that is this is the piece of the detector. And then, if we calculate the solid angle of this, then it's not so small. And then, if you go very forward and you have intense beam, then you are dead. Like, the detector is dead.
And then your nice detector that you spend all this time. Characterizing is no use anymore. Yeah. Okay. Thank you.
Any other question? Okay. So if not, okay, time's up. So thank you very much for the nice talk.
Thanks.
So from the organization.